This is our scientific notation lesson for the Algebra 1 summer math work. We should be starting on page 3 of our booklet, following along and taking notes. Scientific notation is a really useful topic in math and science overall. It's where we take really big numbers or really small numbers that have a lot of place values and format them in an easier to use way, easier to write, easier to keep track of. So rather than writing out all these zeros that represent place values, we condense them into powers of 10. We use powers of 10 because we use a base 10 number system. So a power of 10 coordinates with our place values. There's a few rules for scientific notation, and we see it with this structure here, where we have c times 10 to the nth power, right? So the 10 to the nth, that's our power of 10. C represents what we call either our decimal number, so you can refer to that as your decimal number or your decimal part, or its official name would be the significand or the mantissa. I usually use significand or our decimal number. Everybody will know what you're referring to. So in our first example, we have a really small number, 0.00000456. Written in scientific notation form, we're taking all those powers of 10 and expressing it as 10 to the negative sixth. If we remember our negative exponent rules from 7th grade, that's 1 over 10 to the 6, or essentially like we're dividing by 6 powers of 10. And those 6 powers of 10 we're dividing by coordinate to the 6 spaces that the decimal moves to represent that 4.56. So we see that here with 6 spaces or 6 place values. 5 zeros, but it moves 6 spaces, 6 place values to represent our small number of 4.56 times 10 to the negative 6. The reason we move the decimal 6 places to make 4.56 is the rule of our decimal number or our significand, that it has to be between 1 and 10. So there's only one digit to the left of the decimal when we write in scientific notation, being a 4 here. Our second example is a big number, 289 million, right? So to write that more concisely in scientific notation, we see it as 2.89 times 10 to the 8th. That 10 to the 8th, 8 powers of 10, are representing the 8 place values to get to the 2.89. We're taking those 8 powers of 10 and just condensing them as 10 to the 8th, writing an equivalent number. So let's practice that here. We're going to take two numbers in standard form. That's what we call it when we see all those place values. And we're going to write it in scientific notation. So the first thing I like to do when writing in scientific notation is I want to identify those non-zero numbers. Those non-zero numbers are going to make our decimal number or our significand. So I like to kind of just put a box around it. So that's where my eye's focusing. And right now my box says 103. I need to put a decimal point, so I'm making that number between 1 and 10. To do that, I would put it in between the 1 and the 0 to make it 1.03. Now I have my significand or my decimal number. Now I just need my power of 10 part. Because 103,000 is a big number, I know the exponent is going to be positive, right? Because we're making it bigger. We're not dividing by it. And then I just need to look at our place values. I've got 1, 2, 3, 4, 5. So we'd have 1.03 times 10 to the 5th. And that's an important thing to note, is that when our power of 10, when it's positive, we know it's going to be a big number. And when it's negative, it's going to be a small number. So it's going to be less than 1, which we see with example 4, 0.007089. Again, I'm going to box the non-zero numbers, which for this would be 7089. That extra 0 there is irrelevant, so we're going to ignore it. I'm going to put the decimal point between 7 and 0, making it 7.089 times 10 to the, this is a small number, a decimal number, so I know our exponent is going to be negative. Now I'm just looking for the place values. It moved 1, 2, 3 places, so times 10 to the negative third. We can also be given a number in scientific notation form and asked to write it in standard form, meaning we're going to show all those powers of 10, show all the zeros. So we have 2.34 times 10 to the negative fourth, negative exponent. I know that's going to be a small number. Where would I move the decimal point to make this a small number? It would have to move to the left. So it's going to move to the left 4 spaces. 1, 2, 3, 4. And then these are all going to get filled in with zeros. So it moves 1 space to the left to get past the 2, and then there's going to be 3 zeros. So we'd have 0.0000234 written in standard form. Okay. And example 6, 9 times 10 to the 6th, positive exponent, it's going to be big, so we'd move 6 spaces to the right. Because there's no other digits past the 9, I know it's just going to be 6 zeros, 1, 2, 3, 4, 5, 6. And for our numbers that are larger than 1, we need to go put in our commas for our place values, so we can see that that's 9 million. Scientific notation gives us a great ability to compare the size of numbers without using a calculator. So for example, 2.3 times 10 to the negative fifth and 2.3 times 10 to the negative sixth. I quickly know that 2.3 times 10 to the negative fifth is larger than 2.3 times 10 to the negative sixth just by comparing the powers of 10, right? This 2.3 is going to be closer to our decimal point than 2.3 times 10 to the negative 6, making it larger. In this next example, one's written in standard form, one's written in scientific notation. We have the same decimal part, the 4 and the 3, so I just look at our place values. It would be 1, 2, 3, 4, 5, 6. So this would be the same thing, 4.3 times 10 to the negative 6. They would be equal. So down here, we're looking to see if the numbers are written in proper scientific notation form. So if you see any numbers that are written in proper scientific notation form, I just want you to put a check mark next to it. Might be a good idea to pause the video and try it on your own. Okay. So if we look through 0.35 times 10 to the fifth, that's not proper scientific notation form. The significand, the decimal numbers, not between 1 and 10. It's too small. 78.3 times 10 to the 7th, 78.3 is too big. 3.214 times 10 to the negative 5th, that's just right. 10.3 times 10 to the negative 3rd, that's incorrect. 5 times 10 to the negative 9th, that's just fine. 45.9 times 10 to the 6th, that significand's too big. And 60.9 times 10 to the negative 7th, that's too big also, the significand. Okay? Numbers that aren't written in proper scientific notation form can be recycled to be put into proper scientific notation form. One method, which is too long and I don't recommend, is to take that number and put it into standard form. So 0.35 times 10 to the fifth, if I move it 1, 2, 3, 4, 5 spaces, I can see in standard form, it would be 35,000. And then I can rewrite that myself in proper scientific notation form, seeing that it's 1, 2, 3, 4 spaces, that it should be 3.5 times 10 to the fourth. But that can be kind of long. So what we do is we use our idea of shifting our powers of 10, because all it is we're trading powers of 10 back and forth from the exponent part to the decimal part. And that's what we're going to look at here. Okay, so to fix 0.35 times 10 to the fifth, I would need to move that decimal point 1 space to the right. That's like I'm multiplying by 1 power of 10. To go to 0.35 to 3.5, we multiply by 10. I have to get that power of 10 somewhere. So I take it from our exponent, meaning I'm just going to subtract 1 power of 10 there, and I give it to the decimal number, multiplying by 10. That's where we get our 3.5 times 10 to the fourth. Okay, so that's what we would do if our significand's too small. If our significand is too big, like 78.3 times 10 to the 7th, I need to move the decimal 1 space to the left, as if I'm dividing by a power of 10. I'm taking out a power of 10 of our decimal number. It needs to go somewhere, So I'm going to put it to the exponent. I'm going to add 1 there, making it 7.83 times 10 to the 8th. Okay. So 10.3 times 10 to the negative third, it's too small. I need to take out a power of 10, dividing by 10. So I'm going to add that power of 10 back to the exponent. So I'm keeping the same value of the number, just changing the way it looks. And careful, it's a negative. Negative 3 plus 1, negative 2. Okay. 45.9 times 10 to the 6. Again, it's too big. Divide by a power of 10. And then I'm going to give that extra power of 10 I took out to the exponent, making it 4.59 times 10 to the 7th. 60.9 times 10 to the negative 7th, move 1 to the left, add 1. 6.09 times 10 to the negative 6th. Good. Now that we have that skill in place, that allows us to start looking at how we're going to multiply, divide, and add and subtract in scientific notation, right? And this really relies on our exponent rules for our powers of 10. To multiply in scientific notation, we're going to group together the significands. So I'm going to put together the 4.11 times the 5.2, and you can use the little x, you could use the dot. And then for our powers of 10, we're going to use our exponent rule. When multiplying with the same bases, you keep the base, you add the exponent. So that's 3 plus 2 there. I'd use my calculator to do 4.11 times 5.2, which gives me 21.372. Keep the base, add our exponents, times 10 to the 5th. There's our product. But our product is not in proper scientific notation form. So we need to fix it. To fix it, right, we're going to move the decimal 1 space to the left, which is dividing by a power of 10. So we're going to add 1, making our answer 2.1372 times 10 to the 6th. And that would be our final answer in proper scientific notation form. Dividing our decimals is very similar. Again, we're going to group together our decimal numbers, our significands, do our division. Here, order really matters. Keep the order of the problem. And then our rule for our exponents when dividing bases with same bases, our rule was to keep the base and subtract the exponent. Again, order matters. 5 minus 2. So I'd use my calculator to figure out what 1.68 divided by 5.6 is. That gives us 0.3 times 10 to the 5 minus 2 is 3. Here I would really have to be careful if we were working with negative exponents to make sure I had the signs correct and maybe there's a double sign we need to work with. Okay? So we want to notice again, our quotient is not in proper form, so we're going to fix it. This time, our significand is too small. So I've got to multiply by a power of 10 to move the decimal to the right, which means I had to take that power of 10 from the 10 to the third, making it 3 times 10 to the second as our final answer. When we look at word problems with scientific notation, a key phrase that tells us division would be asking a question like, how many times greater something is, or how many times further. That's a key clue for a division in a scientific notation problem. You'll see in the practice portion. Right? Now, addition and subtraction, we left it for last because honestly, this requires the most work with scientific notation, because just like when we're adding like terms, there has to be something to the same, right? I can only add 3x and 5x because they have the same variable, which gives me 8x. But something like 3x and 4y, I can't add those because they're not like terms. It's the same idea with scientific notation, but our like term is having the same exponent, right? So for adding and subtracting, our power of 10 need the same exponent. So if our numbers don't have the same exponent, we need to manipulate them to get to the same exponent. As a rule, I always match the larger exponent. Mathematically, it doesn't matter if you match the larger exponent or the smaller, but by matching the larger exponent, I find we have to do less adjusting of our answers to put them in proper scientific notation form at the end. So we have 2.3 times 10 to the 6th plus 4.7 times 10 to the 4th. They're not like terms because they don't have the same power of 10. I'm going to match the larger exponent. So I'm going to match the 10 to the 6th, which means I have to add 2 to the 4. Okay, I have to get 2 powers of 10. I'm going to get those 2 powers of 10 from the decimal number, the significand. So I have to divide them out, meaning I'm moving the decimal point 2 spaces to the left. When I do that, now I'm going to have 2.3 times 10 to the 6th plus 0.047 times 10 to the 6th. When we add, again, we're going to group together our decimal part. But this time, we're going to keep the base and the exponent because that's that like term aspect. Just like when we did 3x plus 5x equals 8x, right? That variable didn't change. The same idea here. It's just going to be times 10 to the 6th. Maybe I use my calculator. Maybe I just think about it and I see now we're going to have 2.347 times 10 to the 6th. And it is in proper form. So we're just going to box our answers. Okay. So review the video, keep this all in mind as you now practice on pages 5 and 6.